know, the terms that we use in science are used very specifically in science as terms of art, but they have very different meanings on the street, and this is a source of a lot of confusion. When scientists talk about fact, they're talking about confirmed observations, and facts are interesting, but they're not terribly exciting. They don't do a whole lot for you. Facts are a dime a dozen. There's facts all over the place. A hypothesis is a testable statement. You're saying, you know, what's the relationship between this and this? And you go out and test it, and you either accept or reject your statement of that relationship. Hypotheses are very useful. They're very helpful. They help us build theory. Theories are the most important things in science. Theory to a scientist means explanation. And these are logical constructs of facts, of tested hypotheses, of laws, of all kinds of stuff that, taken together and put in a logical descriptive fashion, help us understand some kind of natural phenomenon. Most lay people think that theories are guesses or hunches or something that you don't have to take terribly seriously. It's not such a big deal. Completely opposite in science. Theories are the most important things in science. What a lot of, unfortunately, textbooks lead people to misunderstand is that a really good theory grows up into a law, as if theories are refined and then become laws, and laws are somehow more important than theories. In science, actually, what a law is a descriptive generalization. So we talk about the laws of thermodynamics that tell you about heat under different circumstances. You hear about the laws and study the laws of heredity that Mendel developed, the law of independent assortment and so forth, because theories explain laws. So in general, the hierarchy of explanation is very different in science than it is in the general public. The general public puts facts on top, laws next, hypotheses, and then theories. Maybe theories and hypotheses can move around a little bit. In science, on the other hand, theories are the most important thing. Laws are next most important. Hypotheses are next most important. And perhaps the least most important part of a scientific explanation is facts, because facts are a dime a dozen. And facts don't explain anything.
I'd like to say a few words about how science goes from making observations all the way to turning those observations into theories. And I'm going to naturally reflect my own field of geology. It began by people observing things that we see every day, like rivers, for instance, flowing. And people began to notice that big rivers tend to flow in big valleys. They notice that rivers get bigger downstream. They notice that when tributaries come into a mainstream, they generally make an angle that points upstream, and so on and so forth. These are observations. And after you make enough observations, you realize that these are scientific facts. It's not always true that they make an acute angle, but it's true enough so that when you find they do not make an acute angle pointing upstream, you know there's something happened. Something has happened of geologic interest there. So we have observations, and gradually they turn into facts. Somebody a long time ago noticed that the sun rose in the east and set in the west. And after a while, that becomes a fact, and we can be absolutely certain that tomorrow the sun is going to rise in the east and set in the west, and you and I would stake our life on that. Right? Right. But why? It appears that the sun moves around the earth. And Ptolemy worked out a theory that had the earth at the center of the solar system and the sun working around, revolving around it, and everything else, that lasted for many, many centuries and explained things pretty well, but not quite well enough. And so at some point, another person, Copernicus, got the idea that it might be the other way around, and maybe the sun is at the center of the solar system and the earth is going around the sun, and so are the other planets. And so there was an observation, there was a fact, but the hypothesis of Ptolemy, or you might even have to call it a theory since it lasted so long, was then replaced by another theory. So to get to a theory, you have to have something that explains all the known observations, the facts, that survives the test of time, that has predictions. Like if you accept Copernicus's theory, then you can predict the motion of the planets. And when you look at the motion of the planets, astronomers do that, they find that they meet much better than they did with Ptolemy's system, the observation. So science progresses from observation to fact, then some explanation, a hypothesis, and then once the hypothesis is supported, corroborated over and over and over, it becomes a theory. And we've seen this happen in geology where continental drift was rejected, rejected, rejected. Then suddenly, at one meeting almost, one scientific meeting, it was accepted in a new form, plate tectonics. This was about 40 years ago. And plate tectonics is now a very strong theory. It's been around 40 years. Evolution has been around for 150 years or so. And no one has ever disproven it. If it's wrong, why can't it be shown to be wrong? It may be wrong. Someone may show it wrong tomorrow. Someone may disprove or falsify plate tectonics. I would be totally shocked and amazed, but I have to admit as a scientist that it's possible.